we are on Unit 4, Lesson 5. So it's the sum, difference, and double angle identity lesson. So we can look here at lesson objectives. It says we're going to use the sum, the difference, and the double angle identities to evaluate trig expressions, verify trig identities, and solve trig equations. So yes, that is in fact what we are going to do. And in order to do that, we first need to talk about the formulas. So here are our sum and difference identity formulas. These are on the yellow sheet, so you will have those sitting in front of you. So notice here we have sine of A plus B. So if you have a plus sign between two angle measures, so it's a sine of some angle measure plus a different angle measure, and that's going to equal sine of the angle measure, the first angle, times cosine of the second angle. And then if it's a plus sign, it's a plus sign here as well, plus sine of the second angle measure times cosine of the first angle measure. So what is the difference? Well, if you have a minus sign separating those two angles, A minus B, then you're going to have a minus sign in this equation instead. So that plus minus, they're measuring up, they're matching up with each other, right? So if it's a minus sign here, it's a minus sign here. If it's a plus sign here, then it's a plus sign here. So that's the way you're reading all those formulas. You should be reading them just like that. So cosine of angle A plus angle B would be cosine of angle A times cosine of angle B minus sine of angle A times sine of angle B. And if there's a minus sign between those two angles, then there's a plus sign over here in the formula. And then you see over here tangent of angle A plus angle B. We have a plus sign in the top and a minus sign in the denominator. So tangent of A plus tangent of B divided by 1 minus tangent of A times tangent of B. And then, of course, if you have the minus sign, it's a minus sign on top, but a plus sign on the bottom. Now, what is not on your formula sheet, which we're going to show you how to get now, is the double angle identities. So if you want to know how to, or you have to use the double angle identity, you're trying to find sine of 2A. Well, that just means sine of A plus A. So you're going to have to develop this equation on your own because it's very simple and straightforward. We hope that's what you see here when we do this example. So sine of twice an angle is just sine of A plus A. Well, instead of having A plus B up here in this formula, we're just going to put in A twice. So we're going to get sine of the first angle measure times cosine of the second angle measure, which happens to be A as well. And then if we have a plus sign here, we keep the plus sign up there. So it's plus sine of angle A times cosine of angle A. So again, what did I do? I just used this formula up above. They have the first angle and the second angle. So all I did was have the first angle, and the second angle here and here. And so we end up with sine A cosine A plus sine A cosine A, which is just 2 sine A cosine A. So sine of the double angle, sine of 2A is equal to 2 sine A cosine A. How did we get that? We just put in A for B, so it's A plus A. So everywhere you see a B, you would substitute in for an A in this formula up here, and this is what we get. All right, for cosine of 2A. Cosine of 2A, again, I'm going to put in cosine of A plus A. So there's no B's in this formula. So because it's a plus sign, I'm going to have a minus sign in between, and all these A's and B's are just going to be A's. So I'm going to get cosine of A times cosine of A minus sine of A times sine of A. So that's cosine squared of A minus sine squared of A. So this is the double angle formula. Cosine of 2A equals cosine squared minus sine squared. Now, we can create two other equations from cosine of 2A, because if we substituted in for cosine squared, remember cosine squared is equal to 1 minus sine squared of the angle. So cosine squared A is equal to 1 minus sine squared A. So if I substitute in 1 minus sine squared A for cosine squared, I'm going to get 1 minus sine squared to give me 1 minus 2 sine squared A. So this is a second example of a formula we can use. Whoa, I don't know what just happened. My bad. So now we have the first one, which is cosine squared a minus sine squared a. We have the second one, which is 1 minus sine squared a. And then, of course, we have a third one, because sine squared a is equal to 1 minus cosine squared a. So where I see my sine squared down here, I'm going to substitute in 1 minus cosine squared. But if I substitute in 1 minus cosine squared a here, I have to distribute this negative sign. So that's going to give me a minus 1 and a plus cosine squared. So this time I'm going to get a positive 2 cosine squared a minus 1. So that is my third formula I could use for cosine of a double angle, or cosine of 2a. So one is cosine squared minus sine squared, one is 1 minus 2 sine squared, and one is 2 cosine squared a minus 1. And I will kind of explain when we do other example problems why you might want to use one over the other. But again, none of these formulas, these double angle identities, are not on the formula sheet. You have to be able to derive them. You have to be able to develop them on your own by just simply replacing all of your A's and all of your B's, right, with A's up here. Okay. I don't know why that's not erasing. All right, and then we have finally our tangent of 2a. So tangent of 2a, we're just going to substitute in A's everywhere up here, because that's tangent of a plus a. So that's going to be tangent of a plus tangent of a divided by 1 minus tangent of a times tangent of a. So if I simplify that, I'm going to get 2 tangent of a divided by 1 minus tan squared a. So I have my double angle identities. We're going to use those. Any problems coming up? All right, so here are examples we would see where we would use the sum and difference identity. So first we're going to start with sum and difference. So this first one right here, it says simplify the expression cosine of theta minus 3 pi over 2. So theta is like A and 3 pi over 2 is like B. So it's cosine of A minus B. Well, we just learned that cosine of A minus B excuse me, is equal to cosine of A, the first angle, times cosine of the second angle. We switch the sign, and then it's sine of the first angle times sine of the second angle. So I'm just going to substitute in. So it's cosine of theta times cosine of 3 pi over 2 plus sine of theta times sine of 3 pi over 2. So where is 3 pi over 2? That's here, where your ordered pair is 0, negative 1. So cosine of 3 pi over 2 is equal to 0, and sine of 3 pi over 2 is equal to negative 1. And so 0 times anything is equal to 0, and negative 1 times sine is equal to negative sine. So my answer there is just negative sine theta. So this equals negative sine theta. All right, example 2, it says find the exact value of cosine of u plus v, given that sine of u is 12/13 and u is in the first quadrant. Cosine of v is negative 3/5 and v is in the second quadrant. So what you should do is you should draw a triangle for u and v. So it says u is in the first quadrant. So I'm going to draw my triangle with angle u here, because it says sine of u is equal to 12/13. That's opposite over hypotenuse, or y over r. So I need to find my x value. So x squared plus 12 squared equals 13 squared, or you just recognize that this was a Pythagorean triple, 5, 12, 13. It is in the first quadrant, so x is going to be positive. So now I know that x is equal to 5. You might be saying, hey, why do we have to do that? Well, I guess we should have probably gone ahead and said, okay, if we just wanted to solve cosine of u plus v and plug it into the formula, we would have said cosine of the first angle times cosine of the second angle, change the sign, so minus sine of the first angle times sine of the second angle. But we only have sine of u, so we know sine of u is equal to 12/13, right? We only have cosine of v. Cosine of v is equal to negative 3/5. So we're missing cosine of u and we're missing sine of v. So that's why I had to do this special case triangle. So now if I want to find cosine of u, right, it's going to be 5/12. So when I see cosine of u, I can put in 5/12 because it's adjacent over, 5/13 because it's adjacent over hypotenuse. So now I need to draw the other triangle, right? So I'm going to draw here my V triangle. So we said that's in the second quadrant according to this information right here. So I'm going to use my red. So cosine of V is adjacent over hypotenuse, or x over r. So I know I have a negative 3 for my x, which makes sense. I'm going to the left for my quadrant 2. And my y is going to be positive. So some of you might recognize that this is a 3, 4, 5 triangle. So y is going to be 4. So sine of v is opposite over hypotenuse, which is just 4/5. So now I simplify this. So remember, you're multiplying these fractions to each other according to the formula. So I'm going to get 5/13 times negative 3/5. Do not cancel this time. Usually I recommend you cancel, but don't do that because we already have a common denominator right here. So you can just keep the common denominator, see what their numerators are, and then we can simplify really easily because we have a common denominator. So we have negative 15/65 minus 48/65, and that becomes negative 63/65. So this is how you're going to use the sum and difference identities. It's very abstract today, this lesson, but we're just plugging into that formula and simplifying our answers. All right, moving on. So here's another type of question we like to give to you. It says find the exact value of sine of pi over 12. So you can't find an exact value of this, right? We don't know how to do that. So we are going to use the sum and difference identities to do that. We know 3 special case triangles. We know root pi over 4, which is root 2 over 2, root 2 over 2. Pi over 3, which is 1/2, root 3 over 2. And pi over 6, which is root 3 over 2, 1/2. So we know these 3 special case triangles. And all 3 of these special case triangles can be rewritten as 12ths. 1/4 is the same as 3/12. 1/3 is the same as 4/12. And 1/6 is the same as 2/12. Now look, we can use a combination of 2 of these 3 angles to add or subtract to get pi over 12. And we have options. So just because I do one option doesn't mean you have to do what I do. You could do something else. So we can either do sine of what? Well, we could do 4/12 minus 3/12, so pi over 3 minus pi over 4. Or we could do sine of, well, I could take 3/12 minus 2/12, so pi over 4 minus pi over 6. So I'm going to pause here. I think you should pause, try one or the other, and see if you get root 6 minus root 2 over 4. So that's what your answer should be. I'm not going to do it for you. You choose one of these 2, follow the formula, and you should get root 6 minus root 2 all over 4. All right, example 4. So example 4, we're back to, we want to find tangent of a double angle. So you're going to have to go back and look at that tangent of a double angle formula. So we had the tangent of 2a equals 2 tangent of a, which in this case is theta, divided by 1 minus tangent squared of theta. So that is my double angle formula for tangent. Now because we gave you sine of theta is equal to 5/7 and it's in the second quadrant, I'm going to draw my special case triangle, my triangle, that's not a special case, where I have theta here in the corner and I have my opposite, which is 5, and my hypotenuse, which is 7. So I'm trying to find my x value because I want to get tangent, and tangent is opposite over adjacent, or y over x. So I have to do x squared plus 25 equals 49. Therefore, x squared is going to equal to 24. So x is going to be plus or minus root 24. Well, because we're going to the left, it's in the second quadrant. Hopefully you are saying, yep, that means it's negative root 24. So I plug that number into this formula, right? So you go ahead and do that. I'm not going to do that for you. But when you get your final answer, I will tell you the final answer. It should be negative 240 divided by root 24. So go through, plug it all in, simplify, you have a complex fraction, try to finish it, and then you should get negative 240 divided by root 24. You do not need to rationalize the denominator. You can keep it like this. If you'd like to rationalize the denominator, you could simplify that, which simplifies to negative 10 root 24. But if you don't want to have root 24, it could be negative 20 root 6. Like, there's all kinds of possibilities, but this is fine for us. Okay, so how else are we going to use the sum and difference identities? Well, we're going to use them for our verifications or for our solving. So example 5, it says we're going to solve cosine of 2x plus cosine of x, and notice there's no domain restriction, so we're going to have to find the general solution. So this is now where we had a choice. Our choice for cosine of 2x was either cosine squared minus sine squared, or it was 1 minus 2 sine squared, or it was 2 cosine squared minus 1. Well, because we're solving, it only makes sense to try to get everything into the same function. We have an extra cosine of x here, so I'm going to put everything in terms of cosine so that I can factor, because now when I see this cosine squared, no matter what, I'm going to have some kind of squared, which leads me to believe I'm going to be factoring because I have a cosine to the 1 power here. So I am going to choose to substitute in 2 cosine squared x minus 1 for this cosine of 2x. And then I'm going to rewrite plus cosine x equals 0. Now, hopefully you're seeing right away that we can factor this problem. I'm going to reorder it, right? Where cosine of x, we can say that's going to equal a. So we have 2a squared plus a minus 1 equals 0. So this is your a squared, this is your a, and so now I'm factoring this quadratic equation. Well, 2a squared, that's a prime number, so it's 2a times a. 1 is a prime number, so it's 1 times 1. We just have to figure out which one is positive and which one is negative, right? And because I want this positive 2a minus a, so my plus has to be over here to the right with a, and my minus has to be here. So a is going to equal 1/2, or a is going to equal negative 1. But remember, it wasn't a, it was actually cosine of x. So cosine of x equals 1/2, or cosine of x equals negative 1. And so now I'm going to solve that. Well, when will cosine of x equal to 1/2? That's when we have a pi over 3. And remember, cosine is positive in the first and fourth quadrants. So that's pi over 3 and 5 pi over 3. When will cosine equal negative 1? Cosine is associated with the x value, so it's over here at pi units. And then remember, it is the general solution. So we need to do pi over 3, 5 pi over 3, and pi, plus 2 pi k, where k is an element of the integers. So that is our final answer. So we're going to use those double angle identities for solving, but we're also going to use them, as you can see here in our next example, for verifying identities. So our left-hand side has cosine to the fourth minus sine to the fourth, and our right-hand side is a double angle identity. You can work with either side. I am going to choose to work on the left-hand side because I immediately see this is the difference of squares, right? Cosine squared times cosine squared is cosine to the fourth. Sine squared times sine squared is sine to the fourth. So I am immediately going to factor. So factoring, I'm going to get cosine squared x minus sine squared x times cosine squared x plus sine squared x. Right? Difference of squares. So it's the square root of cosine to the fourth minus the square root of sine to the fourth, etc., and then plus and minuses. Well, hopefully you see right away what do we know? We know that cosine squared plus sine squared is equal to 1, right? So my next line is just cosine squared x minus sine squared x equals cosine of 2x. And look at your formula sheet, right? When you derived that, cosine squared minus sine squared, that's up here, right? Look at that. It's one of our 3 formulas, so that is equal to cosine of 2x, and cosine of 2x is equal to cosine of 2x. We're done. Not so bad. Maybe it looked a little frightening, but it really wasn't that bad. Okay, this is a level 4 question. I just want to come right out and say that. I skipped example 6 and did example 7, and example 6, I would just say it's a level 4. It's challenging, it's interesting. You can definitely get to the answer, but I'm not going to lie, it's a level 4. So my advice to you is to expand to the left-hand side. See what happens. I'm not going to go through all of that here on this video, but we can certainly any teacher will certainly take you through it, and you can look at the answer key for some hints, but my hint to you, step number 1, is to expand. Expand here on the left-hand side, and then go from there. All right. We go back to this level 4. There is an interval here, so when you think you have all of your answers, you probably don't. So you need to think about that and make sure you have all the possible answers from 0 to 2 pi. It's an interesting question. All right, hopefully that was good. We'll see you later. I'm also not going to do this for you. True or false? I'm going to tell you both right here. They're false. Figure it out. Use your sum and difference identities and see if it equals the left-hand side equals the right-hand side. So expand using your identities, and then see if they equal it. They don't. So go ahead and try that on your own. And finally, recall from Algebra 2 Trig that in order to verify algebraically whether a function is even, odd, or neither, you need to replace x with the opposite of itself, so negative x. And then when you plug in a negative x, you see is the y value its original. If so, then it's even. If the y value is its opposite, then it's an odd function. And if the y value is neither its original or its opposite, then it is neither an even nor an odd function. So for example 9, it says verify algebraically if f of x equals sine of pi over 2 minus x is even, odd, or neither. So what do we need to do? Well, we need to first expand and see what's going to happen here when we let's use our difference identity for sine. So sine of pi over 2 times cosine of x. We keep the same sign. We do sine of the second angle times cosine of the first angle. And I'm going to simplify this. So sine of pi over 2, right? Pi over 2 is up here. It's 0, 1. So sine is equal to 1. Cosine is equal to 0. So what do we get? We get 1 times cosine and negative sine times 0. So we just get cosine of x. So this whole thing simplifies to cosine of x. If I put in the opposite of x, this is f of x equals, oops, sorry, I don't know how my colors are changing here. So f of negative x equals, well, we need to put in the opposite of x. So that is pi minus a negative 2. Well, minus a negative 2 is just a plus, right? So now I'm going to use the same formula, except I have to put a plus sign in there instead of a minus sign. So I'm going to get sine of pi over 2 times cosine of x minus plus, because we have a plus sign, sine of x times cosine of pi over 2. Well, again, this equals to 1, this equals to 0, so did anything change? No, it's still equal to cosine of x. So because when I put in the opposite of x, I got the original y value, I know this function is even. Or I could have just said f of x is even. So when I plug in, I look at the original, I simplified it, I got cosine of x. When I put in the opposite of x, I simplified it, I still got cosine of x. So when I put in the opposite, I got the original y value, therefore this function is even. All right, that's it. Hopefully everything went well. That level 4, it's very interesting. It's doable. Just keep working through it and ask your teacher questions. We go back to that